Hi, and welcome to Energy Year 9 Lesson 4. My name's Mrs. McGee, I'm one of the Science Directors, and today's lesson is about efficiency. Now, before we start this lesson, you will need a paper or an exercise book and a pen. You will also need a calculator, and if you're doing this lesson at home, remember that you need to try and avoid distractions. So put your phone away unless you're using it to watch this lesson, but make sure that you turn notifications off. So our starter today is to see what you can remember from a couple of lessons ago about kinetic energy and gravitational potential energy. So in this picture here, you have two sets of graphs, and these graphs show the kinetic energy and the gravitational potential energy stores of the skateboarder, and also the thermal energy store of the surroundings. So the graph on the left shows the energies when the skateboarder is in position A. So that's at the very top of the ramp. So it shows you how much kinetic energy, gravitational potential energy, and thermal energy there is. And then the graph on the right shows the energies when the skateboarder is in position B. So that's near the bottom of the ramp. So the skateboarder has just come zooming down the ramp. So again, look at the kinetic energy, the gravitational potential energy, the thermal energy of the surroundings, remember? And then it also shows you the total energy of the whole system. So using this information, I'd like you to answer the following questions. Describe the two main energy stores of the skateboarder at the top of the ramp. How do these change as she skates down the ramp? What happens to the thermal energy store of the surroundings, again, as the skateboarder skates down the ramp? And why does this happen? So I'm going to give you 3 minutes to do this. Off you go. Okay, so let's see how you did. Grab a different coloured pen if you have one, and let's go through these answers together. So the first question asked you to describe the gravitational potential energy store and the kinetic energy store of the skateboarder at the top of the ramp. So at the top, the kinetic energy store is empty because she's not yet moving. So the skateboarder is not moving yet, therefore no kinetic energy. The gravitational potential energy store is full because she is at the highest point on the ramp. So that is her maximum gravitational potential energy. Number two, how do these energy stores change as she skates down the ramp? So the kinetic energy store will increase because she's speeding up, but the gravitational potential energy store will decrease because she's getting closer to the ground. So question number three, what happens to the thermal energy store of the surroundings and why does this happen? So the thermal energy store of the surroundings increases as a skateboarder moves down the ramp. And this happens because of friction and air resistance. So that's friction between the wheels of the skateboard and the ramp, and then air resistance as the skateboarder is moving through the air. So what happens is that some of her stored energy is lost or transferred to the surroundings through heating, which is what increases the thermal energy store of the surroundings. So in today's lesson, we are first going to describe what efficiency is, and we're going to look at different examples of appliances that are more or less efficient. And then in the second part of the lesson, we're going to apply two different equations to calculate efficiency. So let's have a think now about what efficiency is. I'd like you to imagine that you have this huge field with really long grass, and someone is asked to cut the grass in this field, but they are given a pair of scissors to do this. Okay, so can you explain in terms of energy why this process is not efficient? So you don't need to write this down, but just have a think about this. And then have a think about how could you make this process more efficient and why would that help? So again, jot some ideas down if you want to, but you don't have to. Just have a think about it and I will give you a few moments. Okay, so hopefully you thought of something like the fact that this process will not be efficient because that person will actually be wasting a lot of energy. So they have to walk up and down this field, and so they're transferring, they're using that energy as they're walking up and down the field, but very little of their energy that they're using is actually being transferred to the scissors to cut the grass, and so they're wasting a huge amount of energy. How could we make this process more efficient? You give them a lawnmower, so they're still walking up and down the field, so they might be using the same amount of energy or a similar amount of energy, but more of their energy is going to be transferred to the lawnmower, which has got bigger blades, which is going to be cutting more grass. So that will make the process more efficient. So if we think about another example now, let's think about a light bulb. So let's imagine that this light bulb uses 100 joules of electrical energy. So 100 joules of electrical energy is transferred to this light bulb. Now that light bulb then gives out 25 joules of light energy. So it transfers 25 joules of light energy. But that's not all of the energy that it took in. So somewhere there is another 75 joules of energy. Now, we know from our experience that light bulbs also get hot as they are being used. So that is thermal energy. So the light bulb also transfers 75 joules of thermal energy to the surroundings. Okay, so you'll notice that these 25 joules of light energy and the 75 joules of thermal energy add up to 100 joules, and that is how much electrical energy was transferred to the bulb. Now this is important because if you remember from earlier lessons, energy cannot be created or destroyed. We call this conservation of energy. So all of the energy that goes into an appliance has to equal the amount of energy that comes out of the appliance as well. It just so happens that here the bulb is transferring two types of energy, so light energy and thermal energy. Now, this thermal energy here isn't useful energy for the bulb. Okay, so the light bulb is wasting that thermal energy. The light energy that is transferred from the bulb is useful because that's what a bulb is designed to do. It's meant to light things up. So we can name these different energies. So our 100 joules of electrical energy is called our input energy. So that's the energy that goes in to the bulb. And the light and thermal energies are known as our output energies. Now the light energy, remember, is our useful output energy, and the thermal energy is wasted output energy. So this bulb here wastes a lot of the energy. So it is not very efficient actually, because it's wasting 3/4 of the energy that went into it. So I'd like you now to think about different types of input and output energies that we can have in different appliances. You've got a list of different energies here in the top right hand box that you can use to answer these questions. So I'm going to do the first one with you. So in our light bulb, the input energy, so the energy that goes into the light bulb, is electrical energy. The useful output energy is our light energy, because that's what a light bulb is designed to do, is to light things up. And the wasted output energy is thermal energy. Okay, I'm going to give you 3 other examples. So an electric drill, a television, and a car engine. And I would like you to write these down and decide for yourself which are the input and useful and wasted output energies for each of these appliances. You've got 3 minutes, off you go. Okay, so grab your different colours pen and let's go through these together and mark them. So for the electric drill, the input energy is electrical energy. The useful output energy is kinetic, so because the drill moves and that's what we want it to do. And the wasted output energy is thermal energy. There will also be some wasted sound energy. Okay, so you can add sound energy to that. For your television, the input energy again is electrical because we plug the television in into the mains electricity to make it work. The useful output energy is light energy. There will also be useful sound energy, so you can add that if you'd like to. And then the wasted output energy will be thermal energy. Your television gets hot as we're using them, but that's wasted energy. And then finally, your car engine, the input energy, this time is chemical because it will run off the petrol or the diesel that you put into your car, and that is chemical energy or has chemical energy stored in it. The useful output energy this time is kinetic, the main one. There will also be other useful output energies in a car, but the main one is kinetic energy. And then the wasted output energy, again, is thermal because your car engine will heat up as it is being used. So let's go back to the efficiency of this light bulb. Now, what we can do is use efficiency ratings to compare different types of appliances. So in this light bulb, we have 100 joules of electrical energy that goes into the light bulb. Of that, the useful output energy is the 25 joules of light energy, and the wasted output energy is the 75 joules of thermal. So this light bulb actually wastes a lot of energy. It's wasting 3/4 or 75% of the energy that went into it. That's a huge amount. So this light bulb is not very efficient at all. Now let's compare the first light bulb to this second light bulb. This second light bulb still has 100 joules of electrical energy going into it, but you can see on the right hand side that now the light energy, the useful energy, is 75 joules. So that's a lot more than the first light bulb. And this second light bulb is only wasting 25 joules of thermal energy. So that's 25 joules out of 100. So that's 25% or 1/4. This second light bulb is actually called an energy efficient light bulb. So to help compare efficiency ratings on different appliances, you can get an energy efficiency label like the one shown here, and you would get it on new electrical appliances, cars, or even buildings. And the numbers on this label represent percentages. So let's just check that we understand what this label is showing us. I'd like you to do the following questions in your book. So 1, if something is C rated for efficiency, what is the percentage efficiency? 2, what is this efficiency as a decimal? Let's see if you understand percentages. 3, what does it mean if something is 50% efficient? And 4, what would it mean if something was 150% efficient? Ready? Off you go. All right, so grab your different colored pen and let's mark this together. Number one, if something is C rated for efficiency, that means if you look at the label that it will be between 69% and 80% efficient. And you have to use the symbol percentage here because it asks you to in the question. So that's pretty efficient. That means that it only wastes a small amount of energy. What is this efficiency as a decimal? Now, if you remember from your maths lessons, 69% would be 0.69 and 80% would be 0.8. Number three, what does it mean if something is 50% efficient? Well, that means that half of the energy that you put into the object will be transferred into a useful energy form. So half is 50%. So of the energy that goes in, 50% of it will be usefully used, which means that 50% of it will also be wasted. And number four, what would it mean if something was 150% efficient? Well, actually, that would mean that you would get out of the appliance 50% more energy than you put in, and that is impossible. Nothing can ever be more than 100% efficient, because if it was more than 100% efficient, that means that you are creating new energy from nothing, from nowhere, which we know is impossible because energy has to be conserved. So hopefully now you have a much better understanding of what efficiency is and you're able to describe this using different examples. In the second part of the lesson, we're now going to look at two equations that we can use to calculate efficiency. Okay, so we're now going to think about how we would calculate efficiency. So let's just think about what efficiency is again. So let's imagine that this here, I'm going to do a little pie chart, is my total input energy. So it's the total amount of energy that goes into my appliance. Okay, now of that total input energy, a proportion of it is going to be transferred into useful energy and a proportion of it is going to be wasted. And we've seen several examples already where some appliances like regular light bulbs actually waste quite a lot of this total energy, and some appliances like energy efficient light bulbs, for example, will waste a lot less energy. So let's imagine that this total input energy, let's imagine we've got 100 joules of total input energy. So this whole circle represents 100 joules. And then of that 100 joules, let's say that 1/4 of it, so that would be 25 joules, is useful. So it's transferred into useful energy. So this is our output. So useful output. And then the rest of it, the 75 joules, is our wasted output energy. So this could be like our light bulb, our regular household light bulb, which is not very efficient. So what I want to work out is what percentage does this useful output represent of the total input. So of my 100 joules I started with, what percentage is 25 joules of 100? And the way that we do that is the same way that you would calculate percentages in maths. You take the part, so that's my 25 joules, you divide it by the whole, so that's my 100 joules, that's my total input, and you multiply it by 100 to turn it into a percentage. So 25 divided by 100 times 100, in this case, it would be 25% efficient. Okay, so it's my useful output divided by my total input and then multiply it by 100 to turn it into a percentage. So here is the equation that we would use to calculate efficiency. I'd like you to write this down, and if you need a bit more time, then pause the video, that's fine. So efficiency is the useful energy output divided by the total energy input. And if we want to turn this into a percentage, we would have to multiply that by 100. Now, efficiency is usually given as a percentage, or you can also give it as a decimal. And remember that energy is measured in joules. So make sure you've written this down in your notes. Pause the video if you need a bit more time. Okay, so let's do this first calculation question together. A light bulb uses 100 joules of electrical energy and gives out 25 joules of light energy. What is the efficiency? Now, this is the same example of the light bulb that we've been looking at throughout this lesson, so you can see the diagram there as well. So let's first write down what we've got. So the 100 joules of electrical energy, that is the total energy input. So that's what goes into the light bulb. So the total energy input equals 100 joules. Okay, and then the 25 joules of light energy that comes out is the useful energy output. So useful energy output equals 25 joules. So now I'm going to write my equation. So my efficiency, I'm just going to abbreviate it, equals the useful energy output, or useful energy out, divided by the total energy input. So now let's substitute the numbers in. So my efficiency equals the useful energy out, which is this 25 joules, divided by the total energy in, which is here, my 100 joules. And then I get my calculator and I just do 25 divided by 100 equals 0.25. Now, if I want to turn that into a percentage, which is very often what happens, I'm going to multiply it by 100, and that is equals to 25. So I multiplied it by 100 to turn it into a percentage, so my efficiency equals 25, and I mustn't forget to draw the percentage symbol there. Okay, so there is my efficiency, 25%. So now it's over to you. I'd like you to have a go at these 3 calculation questions by yourselves now. Remember to show you're working, and if you need a reminder, just rewind the video to the previous example that I was showing you and watch that again. You've got 3 minutes to do this. Off you go. Okay, so let's go through these together now. Grab your different coloured pen and mark at the same time as I do. So a petrol generator uses 500 joules of energy and supplies 200 joules of electrical energy. What is the efficiency? Now, to work out which ones are the output and input energies, you need to read this quite carefully. So the total input energy, so the total energy in is what the generator uses. So it uses 500 joules of energy. So that's the energy that goes in to the generator. And then our useful energy output is what the generator supplies. So that's what it's giving out. And that's the 200 joules of electrical energy. 200 joules of electrical energy. So now let's write down our equation. So efficiency equals useful energy useful energy output divided by the total energy input. So that would be the useful energy out is 200 divided by the total energy in, which is 500 as efficiency. And I want to multiply it by 100 to give me a percentage. So I'm going to get my calculator and I do 200 divided by 500 equals, and then times 100, which gives me 40. So my answer here is 40%. So this generator is 40% efficient. It's always worth noting that you will never get an efficiency of more than 100%. So if you end up with a percentage of more than 100, then you know that you've probably done this division the wrong way round here. Okay, so question number 3 then. A hairdryer uses a total of 180 joules and produces 170 joules of useful energy and 10 joules of wasted energy. What is the efficiency? So let's have a look at the information that we've got then. So the hairdryer uses a total of 180 joules, so that is our total energy input. So that's the energy that goes into the hairdryer. So a total energy input is 180 joules. And it produces 170 joules of useful energy. So that's the useful energy output is 170 joules of energy. What is the efficiency? So let's write our equation. Efficiency equals useful energy output. So useful energy output divided by the total energy input. So now let's put the numbers in. So the useful energy out is 170 divided by the total energy input, which was 180. And remember, we're going to multiply it by 100 to give us a percentage. So we get our calculator and we do 170 divided by 180 equals, and then multiply that by 100 to give me a percentage, and it's 94.4 recurring percent. So we can round it to 94.4%. And then question number 4. An electric hob uses a total of 1,500 joules and produces 200 joules of wasted energy. What is the efficiency? So our total energy input is 1,500 joules. And now this time we're given only the wasted energy. So we're going to have to do an extra step here. So the wasted energy is 200 joules. So that's the wasted energy output. But we want the useful energy output. So you need to work that out first. And what that's going to be is the difference between 1500 and 200 joules. So if 200 joules is wasted, then the rest of it is used usefully. So we can work out then the useful energy output, which will be 1500 take away 200, and that is 1300 joules. So now we're ready to do our equation. So efficiency equals useful energy out. It's always a good idea to write the equation again. Even if you've done it every time, the more often you do it, the more you're likely to remember it for the exam. So it's divided by total energy in. So efficiency, let's plug our numbers in now. So useful energy out we've calculated as being 1300 joules, and then the total energy in was 1500, and we're going to multiply it by 100 to give us a percentage. Here we go. So 1300 divided by 1500 equals times 100 to turn it into a percentage, and that is 86.6. Now you can't really see it there, but there's a dot above the 6, so that's 6 recurring. So when I round that, I'm going to have to round it up to 86.7. So my efficiency is 86.7 because I'm rounding up percent. Okay, so we're now going to look at the second way of calculating efficiency, which will lead us to the second equation in today's lesson. So earlier on, I showed you this pie chart, and we looked at this scenario where you have 100 joules of total input energy. So that's our whole circle, our whole pie chart. And of that 100 joules of input energy, 25 joules of energy was transferred usefully, so that's a useful output energy, and then that means that 75 joules of energy was wasted. And we worked out that our efficiency would be 25 divided by 100 times 100 to turn it into a percentage, and that's 25%. Now, what would happen if instead of talking about joules, we were actually talking about joules per second? So I'm just going to make a bit of space here. So 100 joules per second is my input I'll just rub that off. So 100 joules per second is the energy that goes into my appliance. Okay, so every second my appliance takes in 100 joules of energy. Well, if every second is taking in 100 joules of energy, then that means that every second it is transferring 25 joules of energy usefully. So this becomes 25 joules per second. And that every second it is wasting 75 joules of energy. So this now becomes 75 joules per second. Now, if you remember from a previous lesson, joules per second, so energy transferred every second, is actually your power. Okay, so power is the amount of energy that's transferred every second. So if I've got 100 joules every second going into my appliance, that is actually my total power input. So rather than total energy input, it's my total power input. And if every second my appliance is using 25 joules usefully, so that's 25 joules per second, again, that's my useful output power. And then here, the 75 joules per second is my wasted output power. Okay, so now we're talking about power instead of energy. Now, if you remember as well, the other unit for power is watts. So we could be talking about 100 watts going into the appliance, 25 watts. So instead of joules per second, it's watts being transferred usefully, and then 75 watts being wasted. Okay, so that's watts now. But even though we're talking now about power, my calculation remains the same because I'm still trying to work out what is the useful power output, what percentage is that of the total power input. So it's still going to be 25 divided by 100 times 100 to turn it into a percentage. So useful output power divided by total input power times 100. So here is the second equation that we can use to calculate efficiency. And you'll notice that it looks actually very similar to the first equation that we looked at, but instead of energy, we're looking at power. So again, write this down in your notes, please. Pause the video if you need to. So efficiency is the useful power output divided by the total power input. And again, you multiply it by 100 to turn it into a percentage. Now this time, because we are using power, we're going to measure that in watts, but efficiency is still given either as a percentage or as a decimal. Make sure you've got this written down before moving on to the next calculations. Okay, so I'm going to do this first question for you using the second equation for efficiency, but the strategy is exactly as we have been using for the previous questions. So the total power input to a pumped storage power station is 600 megawatts. So that's the total, let's write down what we've got. Total power input is 600 megawatts. Now, megawatts, 1 megawatt is just a million watts. Okay, so it doesn't matter hugely in this question that we've got megawatts instead of watts, because if you look further down the question, the next value is also in megawatts. As long as both units are in megawatts here, we're okay. So the useful power output is 540 megawatts. So that's our useful power output is 540 megawatts. What is efficiency? So it's just the same strategy that we've been using all along. So let's write the equation. Efficiency equals useful power output divided by total power input. And then we put the numbers in. So the useful power output is 540 divided by 600, and I'm going to multiply by 100 to turn it into a percentage. So calculators, 540 divided by 600 times 100 equals 90. So the efficiency is 90%. So now it's your turn again. 3 more calculation questions. Remember to show you're working and use the same strategy that I have just shown you for these ones. You've got another 3 minutes. Off you go. Okay, let's see how you did on those questions. So grab your different coloured pen and let's go through these together. So question number 2. An electric drill has a power input of 450 watts and a useful power output of 390 watts. What is its efficiency? So the total power input is 450 watts, and then the useful power output is 390 watts. So write the equation. Efficiency equals useful power output divided by total power input, and we're going to multiply it by 100 to get a percentage. So let's plug in the numbers now. Efficiency equals, my useful was 390 divided by 450 times 100. Use your calculators. 390 divided by 450 equals times 100 equals, and it's 86.6 recurring. So I'm going to round it to 86.7. So efficiency equals 86.7%. Don't forget that all efficiencies will be 100% or less. Okay, you can never have an efficiency of more than 100%. So if you've got a number greater than 100 here, you know that you've probably divided these two numbers the wrong way round. Okay, question number 3. An oven transfers 1000 joules per second of electrical energy into 800 joules per second of useful heat energy. What is the efficiency? Now, don't be thrown here by the units, because joules per second, you might remember from a previous lesson, is one of the possible units for power. Because remember, power is the amount of energy in joules transferred per second. So you don't have to worry about the units here. The strategy is the same. So the oven transfers 1000 joules per second. So that's the total power input. It's our 1000 joules per second, because that's what goes into the oven. And it transfers it into 800 joules per second of useful heat energy. So that's our useful power output is 800 joules per second. So we write our equation again. Efficiency equals useful power output divided by total power input, and we multiply it by 100 to turn it into a percentage. So if I substitute the numbers in now, so efficiency equals 800 divided by 1000 times 100. Get your calculators. So 800 divided by 1000 times 100 is 80%. You may have worked this one out without a calculator. Great if you did. Don't worry if you needed your calculator, that's absolutely fine, because you do get a calculator in the science exam. And our last calculation question for today's lesson. A toaster with 100 watts electrical power input wastes 40 joules of energy per second. What is the efficiency? So this one was a little bit more difficult. Hopefully you noticed the couple of traps that are set to you there. So the 100 watts of electrical power input, so that's the total power input, is our 100 watts. Now the 40 joules of energy per second is wasted. So that's the wasted energy coming out. So it's 40 joules per second. If you remember, joules per second is the same as watts. So you can say that that is 40 watts. So this wasted is actually our wasted power output. So you've got your wasted power output here, but we need the useful power output. So you're going to have to work out the difference between those two. So useful power output is going to be 100 minus 40, which is 60 watts. Okay, as simple as that. So now we can use our equation. Efficiency equals useful power output divided by total power input, and we multiply it by 100 to turn it into a percentage. So efficiency is, let's substitute the numbers in. A useful is this one here, 60 watts, divided by 100 times 100. You use your calculator if you need to, that's fine. You might just spot that that's 60%. Okay, so the efficiency here is 60%. Okay, well done for getting to the end of that lesson. So you should now have a much better idea of what efficiency is, and you should be getting better at using both of those equations to calculate efficiency. So here are the key learning points from today's lesson. If you feel that it will help you, you can pause the video now and add this summary to your notes.